Okay, today what we're going to look at is Chapter 2, Section 2, where it's talking about physical and chemical changes in property. Okay, so the things that you need to be able to answer when we're finished with this is to be able to distinguish between the differences in physical and chemical properties, and we talked a little bit about that today, or yesterday, I'm sorry. When we were talking about physical properties, they were things that you can observe without altering the material. So let's say the color, I better change my color. If you want to observe the color blue, that would be a physical property. So color blue, you can see it without having to have a chemical reaction. But if we go to chemical properties, something like flammability. So flammability, on the other hand, a piece of wood, we know that wood can catch on fire. We know that wood will burn, but in order for you to see that chemical property, there needs to be a chemical process taking place. We need to have a reaction that's taking place. Okay, so that's what we talked about on Tuesday. The second thing that you need to be able to do for Chapter 2, Section 2 is to be able to identify or classify changes of matter as whether they're physical changes or chemical changes. So melting, is that a physical change or a chemical change? Oxidation, is that a physical change or a chemical change? So we'll look at those, and any of those changes that might occur, you need to be able to identify at least 4 indicators that a chemical change is taking place. So real simply put, if you have heat that's given off because a fire is taking place, well, you have a release of energy. That's a pretty good sign that a chemical change is taking place. And the last part, what we'll do is we'll look at calculating that energy gained or lost during a chemical change. So, types of changes. We have physical changes and we have chemical changes. Physical changes, if we go with the very basic example, you have yourself a block of ice. The block of ice, it's a solid. You have a definite shape, okay? So it's not going to be altered. You have a definite volume. It's not going to change. As we add thermal energy to it, what we do is we change the physical state from a solid now to a liquid. That liquid, there is a definite volume, but there is a changing shape. As we pour that same amount of liquid, we have our liquid from the, or I shouldn't say liquid, we have our amount of matter that was in our ice. It is now the exact same amount of matter in our cup, but it's taken on a different shape. Instead of a cube, it might be the shape of a, I don't know, a vase or a wine glass, something of a different shape other than a cube. Okay. Now, chemical changes on the, but what I'm getting at here, and I should have said this, we start out with H2O, and we finish with the exact same chemical composition, H2O. We didn't create anything new. We had the exact same thing that we started with that we ended with. Now, a chemical change, on the other hand, if we have that H2O, we know that H2O you use to put fires out. Well, if we separate, we send an electrical current through some water, and we're able to separate the hydrogen and oxygen from it. So what will actually catch on fire? Well, if we're looking at hydrogen gas, if you've ever been into a hospital, you know that you can't have a cigarette or a flame near a hydrogen tank. And you never should have a oxygen tank near it either. And the reason why is hydrogen will catch on fire, okay? And oxygen supports combustion. So you have two gases, okay, that you could have a fire taking place, whereas before the reaction took place, before the hydrogen and oxygen split off, you had something that put fires out. All right, so in this case, we had not just a change of physical state, we went from a liquid to a gas, but we also changed the chemical properties as well. Okay, so those are some of the things we're going to look at. So what exactly is a physical change? A physical change is where we might alter the substance, change its identities around a little bit. So maybe our color changes, water boils, ice melts. We have dry ice, which is carbon dioxide. So let's say we have my block of CO2 in the solid form. If it sublimes, it changes directly to carbon dioxide in the form of a gas. There's no liquid in between there. All right. So, but the material, the compound, we still have carbon dioxide, CO2. It's just we're changing the state of matter that it's in from a solid to a gas, sublimated. But not all changes that you have are real good indicators of whether we have a physical change or a chemical change. The example that I have down here below, you have potassium chromate. That's this stuff right here. All right, now if you heat potassium chromate up, you notice that as we go from right to left, as we add energy to it, the color of that potassium chromate starts to change from a yellow to an orange to a deep orange. But then when you remove the heat, it goes right back to the same color. That's a physical change. We didn't end up with anything new. We started with the potassium chromate. We ended with the potassium chromate. Nothing is created. Okay, so make sure you get your material written down so we have their identifying properties and remain unchanged for this. All right, let's go to the next one. We have chemical changes on the other hand. So chemical changes, you start out with one material. We have a chemical reaction that occurs. Now, in a chemical reaction, we might have what's called a single replacement, or we might have what's called a double replacement. We might have combustion. We might have decomposition. We have all kinds of different ways that chemical reactions are going to take place. In the in during those changes, what we end up with is something completely different. All right, the example I gave you before, you had the water. It was in the liquid state, put out fires, and then when it separated, we had two gases that supported combustion, would actually catch on fire. So I want to give you another example here. If you have ammonium dichromate, now it's a different material, so you have ammonium dichromate, and we heat this stuff up. If you add some energy to it, this is a pretty wild reaction, because once you add enough activation energy to it, what will happen is you'll get a very violent reaction. And one of the gases that you can smell from this, if you can imagine, you have ammonium dichromate. One of the gases that you would smell during this would be ammonia. Now, I can't show you this chemical reaction because one of the byproducts of this is pretty hazardous to you. It's a known carcinogen, so we can't do that in the class. But if I can get the video to work here, we'll open this up. So you add a little bit of heat energy to it. Now, during this reaction, I think it looks kind of like a composite volcano erupting. But all that ash that's being sent up into the air, you definitely don't want to bring that in. But while you're watching this, notice what changes occur here. Right? You have fire, you have color change. If you can imagine, there'd be heat that's going to be given off from this. And look at the difference in the volume of your material. So if those things changed, now we're not going to test out the material to see if it's cancer causing or not. We're going to just trust that the material that I got that from, that they're telling us the right thing. But the other items we can see just from the video that happens. So some real good indicators that what you witnessed there was definitely a chemical reaction. Well, first, in a very good example of an indicator, all right, one of our, and I'll give you some that are good indicators and some that aren't as good. If you have a release of heat energy, so you have a fire, in that example of our ammonium dichromate, as it was ignited, you could see the fire that was coming off of it. So if there's fire that's given off, or heat that's given off, you see light. Okay, that was the red. You had heat. We know that when there's a fire, you've got some heat associated with it. All right, so those are two very good indicators that you have a chemical reaction that's taken place. If we look at the next one, this one, don't confuse this with the bubbles that you get from water boiling. That's dissolved gases that are escaping your water. That's not the production of a gas. When we're talking about a production of a gas, a very common one that you guys might have seen or maybe done yourself, if you take vinegar. Yeah, vinegar, that's acetic acid. You mix it with baking soda, you get your volcano that erupts. Well, one of the gases that you get from that is carbon dioxide. All right. Another example of that, the production of a gas, I told you that you can take your humidifier filters. After a period of time of you using them, they become real hard. The water doesn't filter through the medium as well, or the media as well. And then you throw that humidifier filter away, and then you buy another $7 to $10 filter. Well, the hardness of that comes from the mineral deposits in your water. It's calcium carbonate. Calcium carbonate does not dissolve very well in water. And as your water from your humidifier evaporates into your room, it leaves behind on that paper filter calcium carbonate. You can't wash it off. No matter if you use hot water, cold water, you use soap, it will not come off of that paper filter. So what you can do is you can cause a chemical reaction. You put some vinegar, some acetic acid, onto the calcium carbonate, and what you get is you get just a little bit of bubbling. Some carbon dioxide is produced. That's an example of a chemical reaction. Now, another good indicator that you have a chemical reaction taking place when you have vinegar onto your humidifier filter is after you've leave that vinegar on that filter, which has calcium carbonate on it, you'll be able to notice that the fibers are a little more flexible. They're a little softer. And when you run it underneath water, all of a sudden it becomes a little bit clearer, and water can pass through the paper with ease. That's because what you've changed that calcium carbonate to, you've changed one part of that into carbon dioxide, and then two, you change the rest of that into calcium acetate. Calcium acetate easily dissolves in water, so you rinse it away, and you got yourself a new filter. All right, so it's two different things. All right, this one right here, our precipitate. In the previous weeks, I showed you where you take your lead nitrate and you added to it the potassium iodide. That would be those two clear solutions. Now, when we mixed them together, you ended up with lead iodide, that was the real bright yellow. It looked like a powder that was at the bottom of your beaker. And potassium nitrate. Well, that yellow powder stuff, that lead iodide, that's the precipitate. Okay, so you take two clear liquids, you mix them together, you end up with a solid that forms. That's your precipitate. In those examples that I've given you right now, one of the absolute best indicators is, has your chemical properties changed? If you have altered the chemical properties of that material, you do not have the same thing, then you definitely had a chemical reaction taking place. Now, let's look at some that aren't as good of indicators of a chemical reaction. Color change. In that first example, you saw that the yellow changed to a darker color. That was with your potassium chromate that was being heated up. So once you removed the heat, the color came right back. Electrical current, if you have electrical current that's produced, a pretty good indicator of it. Volume change. Be careful with volume change if we're looking at this, because if you take water in the liquid state and you freeze it, what happens to its size? It gets bigger. So if you go strictly based on this and you say volume change, it got bigger, so it must have been a chemical change, you'd be wrong, because we have to look at the bigger picture. That water in the liquid state, it's H2O. When it froze, the volume did increase, but what is the chemical makeup? H2O. All right, you have a change in taste or smell. Those would be possibilities, but from lab safety stuff, we're not going to ever taste any of the stuff in our room or smell it. I guess if we do an esters lab, I might have you waft the smell to you, but you never stick your face right into a container to take a whiff. That'd be very bad. All right. The next thing, if we have a change in the melting points or boiling points, that could be, now notice I'm saying that could be an indicator that you had a chemical reaction. So ultimately, if you have a change in your chemical makeup, you have something new that's being created, definitely you've had a chemical reaction taking place. Now, in all of those, it doesn't matter what type of chemical reaction that you're having. Everything in terms of reactions is going to have some sort of energy transfer. So if we have a match catches on fire. All right, so you got your match stick, it catches on fire. Here we go. You got fire from the matchstick. In this case, you do have a chemical reaction taking place, and the energy that's being released from this, it might be in the form of light, it could be in the form of heat energy, or that initial sound as it lights that, well, that would be another example of a release of energy. Anytime that you have a release of energy right here, that's what we're going to refer to as an exothermic reaction. Exothermic, easy way to remember this, the EX, and think of it as exiting. So if you're exiting a building, you're leaving the building. And in a chemical reaction where we have an exothermic process, we have energy that's leaving the material. We're breaking the chemical bonds, releasing the energy stored in those chemical bonds. Now on the flip side of this, if you have an absorption of heat energy, energy is going into the system. This is what we refer to as an endothermic. An endothermic is where energy is going into the material. So let's say photosynthesis. Photosynthesis would be an example. Let's see another one. You have an ice cube that's on top of your desk, and it's absorbing thermal energy, warming. That would be an example. All right, so if you're observing chemical reactions, you should be able to identify what are some of the terms that we're going to use for this. All right, so what are some of the terms that we're going to use? Well, we're going to use reactants. We are going to use products. And I want to have an example, and I do want you to put this down on your paper because we are going to balance out a few of these equations. And we're going to look at just some simple laws that we have to follow for this. So we'll use this thing right here. We'll use hydrogen and oxygen. You light a match, you have combustion taking place, and you get water. All right, you get some water vapor from that. So if you have hydrogen gas, it's H2. Now you might wonder, why did I put down H2? Why didn't I just write down H? When we look at some of the elements on the periodic table, there are some elements that you're never going to find in nature by themselves. Now, here you go. It's kind of like that guy or girl that's in high school that as soon as they break up with somebody, bam, they've got another boyfriend or girlfriend. Okay? So hydrogen is like that person that's never, ever, ever without somebody else. So hydrogen is what we refer to as one of our diatomic elements. You're never going to see it by itself. All right? And on the periodic table that I gave you, I list out the 7 diatomic elements. Now, we'll get back to our formula. We have hydrogen and oxygen. Okay, so hydrogen and oxygen are our reactants. Okay, so these guys right here collectively are our reactants. And we're going to add them together. Now you're going to notice something. Why in the world did I put O2? Because O2 is like that other person in high school that's never without a significant other. So you light a match. You light a match, what happens? You get combustion, you get the release of some thermal energy, some light, and what else do you get? You get some water vapor. All right. Now that water vapor is what we refer to as our products. Okay, so I'll put right here, this is our product. So you have the reactants. Those are the things that are going to react with each other, and they're going to produce water. Now this little arrow in between here, this thing, it's not an equals, it's a yields. It's a yields. Okay, so we need to use the right term for this. So yields. Now, yes, we did have an exchange of energy that took place. Okay, so we have to have an understanding that whenever you have a chemical reaction that takes place, you have to obey the law of conservation of energy. Whatever the amount of energy that you start with in a chemical reaction is what you're going to have afterwards. So some of the energy that was released, okay, where did it come from? It came from what we had at the beginning, okay? The second law that we have to have an understanding of is the law of conservation of matter. You cannot create and you cannot destroy matter. You can rearrange things, you can get it to react with each other and form new things, but you can never create or destroy. So, where do we have a problem with this equation that's written up here? All right, so I'm going to change over here to green. And we're going to look at the number of hydrogen that you have. H2. I have 2 hydrogen. That's what I start with. On the right-hand side, my products, I have H2. Great. I'm all good. When I go over here to my oxygen, Here is O2. And on the right-hand side, I only have one oxygen. Small problem here, right? You have broken the laws of physics. You can't destroy matter. So something has to be changed. Now, the impulsive person would say, well, just put a 2 underneath it. Well, all right, I got a joke for you. You got two guys. They walk into a bar. First guy says to the bartender, I'll have some H2O. Bartender gives it to him. He drinks it. Oh, that was good. Second guy says, you know what? I'll have some H2O too. Bartender gives it to him. He drinks it and he dies. Guys, you can't just put different subscripts underneath and expect it to be the same thing. H2O2 is hydrogen peroxide. That's not a good thing to be consuming. All right? So we can't put a 2 there. What we can do is, instead of us saying that we have one molecule of this, instead of us saying that we have one molecule, how about we change the 1 to a 2? Now, the 2 in front of it, that represents what we call a coefficient, a multiplier. So we're saying that instead of us using one molecule, I have 2 molecules. Now, it's a little easier to put the coefficient in front like that. And what this means right here, by putting the 2 in front of it, it simply means that you have 2 of these. You have 2 water molecules. All right, now let's go back and look at the number of oxygens you have. All right, I have 2 molecules of H2O. I have, wrong thing. I have 1 oxygen here, 2 oxygen there from the 2 molecules. So 2 oxygens, great, I'm set. I'm following the law of conservation of matter. I didn't create or destroy oxygen. Hydrogen, on the other hand, when you have 2 molecules of water, look, you have 2 hydrogen here, you have 2 hydrogen there. On the right side, you only have 2. You got 4 hydrogen on the right side, on our product side, and you only have 2 on the reactants. So, what do we have to put in front? If I want 4 hydrogen, I'd have to, 4 hydrogen in our products, I have to have 4 hydrogen to start with. So I put a multiplier of 2. Now what that means, again, what does this mean right here? It means you have 2 hydrogens to start with. So for every 2 hydrogens, you get 4 hydrogen atoms. You have 2 oxygen, and we end up with 2 molecules of water from that. Okay? So there's a lot of different chemical reactions that we can throw in here. This is just one example. It's an easy one that we can start with, and then we'll go a little more in depth later. All right, so at this point, you got to just ask yourself, what would be 2 good indicators that we have a chemical change taking place? All right, so if you can't think of 2 indicators, what you need to do is make sure that you write down these, not just on the notes, but also inside of your outlines. All right, the outlines, you're going to be able to use those on the test, but if all of your work is here, it's not going to do you any good. Okay, so you have to do a little bit of transferring of information. All right, so before we move on, all chemical changes are going to involve some sort of change in energy, whether it's absorbed or released. And the amount of energy that we start with has always got to equal the amount of energy that we end with. And in any chemical reaction, the amount of matter that you start with is always the same amount of matter that you end with. And we accomplish that by balancing chemical equations as we did here. Okay. So, getting back to our change of energy. We said if energy flows into a system, it's endothermic because it's gaining in energy. So it's increasing in energy. So if it's going to increase in energy into, we're going to say that it is positive. You're adding energy to it. So heat is being absorbed. We're going to get to a formula in a little bit. Now the formula we're going to use for this, we're going to use the letter Q to represent heat energy. All right, so as a system gains heat energy from the surroundings will get cooler. A good example of this could be applied to your air compressor tanks that you have at home. So if you have an air compressor at home, you have the tank, and then you got the motor on the top. Okay. As you have air that is pumped into the tank, those particles, they're all spread out real far at first. There's a lot of energy associated with those particles moving around. So I'm going to say that my energy is representative of the length of my arrows that are drawn here. Okay? When that air gets compressed into the air compressor tank, the amount of energy that those particles have now is less. Okay? Where'd that heat go? Well, you get heat right around the engine. Okay, so heat, we are having a release of energy at the top of your air compressor tank. Now, we're talking endothermic process. That's where energy is going into it. Right now, we have energy that's being released up here. Oh, if I could get the D in there. Now, where do you feel the endothermic process where energy is going into the system? Well, whenever you compress air in an air compressor tank, you always end up with some water vapor that gets condensed and it sits in the bottom of your tank. And if you don't release the valve on the bottom of your air compressor tank, you can rust a tank out from the inside out. So you always drain, or you always should drain, your valve at the bottom, the little bleeder valve there. As you open up that valve, what happens to the air particles? They want to expand outwards. Now, if those air particles expand outwards, the only way that they can do that is if they gain energy. All right, so the particles, as they exit, they need to expand. They're going to expand. They're going to start moving very, very rapidly. Where are you going to get the energy needed to increase the motion of those particles? From the surroundings. If you have your hand, this would be foolish to do it. You could have your hand underneath here for a short period of time. But if you put your hand underneath this, all right, that's an ugly hand. But you put your hand underneath it, your hand, if you leave it underneath there for just a little while, what's going to happen is it's going to start to feel very, very, very cold. And why is it feeling cold? Because as those particles increase in energy, as we have an endothermic process, now notice I said process taking place, it is those particles, those air particles are absorbing energy from your hand. All right, so energy is going into the particles. Another example of an endothermic reaction where energy is going into a system, we're increasing in energy content, is photosynthesis. So with photosynthesis, you have the plants that are going to take the energy from the sun, They're going to convert the carbon dioxide and water into glucose and oxygen. You got yourself a chemical reaction taking place. So, where is the law of conservation of energy? Well, you have the energy from the sun that gets absorbed by the plants. The energy from the plants then is stored in the chemical bonds of the plants. Great. Law of conservation of matter. My formula here, you have carbon dioxide. All plants need carbon dioxide. All plants need water. I didn't put energy in here. We didn't put any values on this, but they do need sunlight. What's going to produce? Our sugars and our oxygens. We have to obey by the law of conservation of matter. Can't create or destroy it. So let's take a look. You have 6 carbon dioxide. That's like us saying 1, 2, 3, 4, 5, and 6 carbon dioxide. See why we put the coefficient in front? It's a whole lot easier doing it that way. All right, so you have 6 carbons. On the right-hand side, you have our C6H12O6. That means you have 6 carbons. All right, carbons are good. We don't want to mess with those at all. We're all satisfied with it. Now, let's go to the next thing. Let's take a look at hydrogen. Hydrogen, 2 hydrogen. On the right side, you have 12 hydrogen. That doesn't work. If you have 12 hydrogen, and on this side, our reactant side, you only have 2 hydrogen here, what goes in front? Well, we have to put a 6 in front here. And I wish I had a little more space. So we'll put 6 right there. If we multiply 6, what do we end up with? Well, you have 6 of our H2s. 1, 2, 3, 4, 5. 6 H2s. Now, if we add all of those up, what do we end up with? 12 hydrogens. 12 hydrogens. Okay. Last thing we have to take a peek at is the number of oxygens. So oxygens, let's use green for this. We have 2, 4, 6, 8, 10, 12 oxygen. Okay. So I have 12 oxygen on the left-hand side. On the right-hand side, I have 6 oxygen there. Okay. So I have 6 oxygen. And then over here, this 6O2, that's like us saying O2. It looks more like a 3. We have O2, 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 1, 2, 3, 4, 5, 6. So if we add all those up, you have 6 more oxygen. 6 and 6 get you 12 total oxygen. Now you have a balanced chemical equation. So on this page, I don't want you to just leave it the way it is because it's not right. You need to make sure on your notes that you add the 6 in front of the H2 to make sure that it is a properly balanced equation. We can't just leave it alone and hope for the best. It's got to be correct. Okay. All right. Endothermic reactions. We have energy that's being absorbed, and when we're looking at that energy being absorbed, we're tending to move from a more orderly state to a less orderly state. It's what we refer to as our entropy. All right, and entropy is just a property that describes how disordered is something. Okay, how disordered everything in nature. I mean, think of yourself when you go home. Do you go home and then intentionally go ahead and put all your stuff away where it belongs? Or do you walk in the house and you just throw stuff down? Well, if you're like my 2 brats, they come in, and I had the one day, my youngest son decided to kick his shoe off. It goes flying through the air, hits my ceiling fan light and breaks it. Yeah, chaos. So everything tends to go to a more disordered state. So here, if we're looking at our entropy, I'm going to jump right here to this. All right. So which one has a greater entropy? Which one has a greater amount of disorder? Is it the ice or is it the glass of water? All right. Now in the ice, everything is in a crystalline format. In the water, those particles are free moving and can take any shape of the container that it's in, right? So which one is more unorganized? Which one is the one that has less order to its system? Which one, that's the same thing as saying which one has a greater entropy. The one that has a greater entropy is the water. Okay. We're going to stop right there, and then we'll look at the rest of the stuff tomorrow. All right.